today. Okay, most of today is about energy. We're going to get into some of that Gibbs free energy stuff to do some calculations. This stuff we've talked about. We said that energy is the ability to do work, and we said it another way, it's also the ability to make things move. We talked about how the sun, at least in terms of biology, is the energy for all, the source of all of Earth's energy, at least the biological energy. We talked about kinetic energy. It's almost always associated with what? Movement. The faster something's moving, the more kinetic energy it has. Today in physics, we're doing a lab about kinetic energy. Turns out it's not just about speed. What else determines something's kinetic energy other than its speed? It's mass. Turns out there's an equation. You don't need to know this equation, but that's the equation to calculate something's kinetic energy. 1/2 mass times what? Velocity. Velocity squared. Speed. Oh, this little box. Yeah. I need it up here, so that's about as far as I can go with it. Potential energy. We're going to associate it with what kind of energy? Stored. A battery. In biology, most of the energy we're talking about is chemical potential energy. Energy stored in the bonds of chemicals like ATP, lipids, sugars, so on. Chemical potential energy. Now we talked about the thermodynamic stuff a little bit last class. The first law of thermodynamics, or the law of conservation of energy, shouldn't be anything new to you. It's the idea that you can't what? You can't create energy, you can't destroy it, but you can convert it from one form to another. We're going to use those two phrases, first law of thermodynamics and law of conservation of energy, interchangeably. Can't create energy, you can't destroy it, but you can convert it. Now remember on that test, some of you said cell respiration creates energy. Not true. Some of you said photosynthesis creates energy. Not true. Cell respiration takes energy from where? Food, and puts that energy where? In the bonds of ATP. Photosynthesis takes energy from the sun and puts it in the bonds of glucose, sugar. Doesn't make energy. Now, biggest part of our time today is going to be concentrating on this second law of thermodynamics, which really deals with a concept called entropy. What did we say entropy was last time? Because we did briefly mention it. Disorder, chaos. Going to talk about second law of thermodynamics really 3 different ways, but all 3 of them really say the same thing. First of all, the most basic definition I'll give you is this one. Second law of thermodynamics says that what is constantly increasing? Chaos. Entropy in the universe is constantly increasing. And we talked a little bit about this the last time, that at least in terms of evolution, that doesn't seem to be true, right? Because we went supposedly from like amino acids to what? Amino acids floating in an organic soup supposedly became what? Bacteria. And then through the endosymbiotic thing, what did we supposedly get? Eukaryotes, and then we got eventually up to complicated plants and animals and fungi and probes, right? That seems like what's increasing? Order. So we're saying disorder. What you got to understand is every time a reaction happens, every time you eat food, some of that food is used by your body to do stuff, to move, to talk, to carry out organic reactions. But every time you use some of that energy, what happens to at least some of it? It gets given off. It's heat. It's wasted. And once it comes off as heat, what's going to ultimately happen to that energy? Can't be used anymore, and it's probably going to end up where? Somewhere in space. It's going to leave the Earth and go out into space, never to be used again. So another way to think about the second law of thermodynamics is this, that the amount of useful energy on Earth is constantly what? decreasing. The amount of useful energy on Earth is constantly decreasing. Or we might say the amount of useful energy on Earth is finite. What's finite mean? Limited. There's only a certain amount of it, and it's constantly decreasing. The third way we might talk about that second law of thermodynamics is what this little blurb at the bottom of the screen says. Energy must be added to a system in order to maintain order or homeostasis. Let's say that Jonathan ends up working on Wall Street. He's a stockbroker and he makes millions of dollars. And then come to find out a few years later, after he's built this huge mansion, we find out that Jonathan has been embezzling, and he pulled what's the guy's name? Got in trouble for all the embezzling stuff. Just lost it.
I can see his face.
I can't see it. Anybody know what I'm talking about? I lost it anyway, not important. But he's been stealing all this money, and they catch him. Jonathan goes to jail for say 50 years. He just built this beautiful mansion, and it just sits vacant for 50 years. Eventually, Jonathan gets out of jail. He comes back. Nobody's even been to his mansion in 50 years. What's it going to look like? It's going to be falling apart, right? Because what hasn't been added to that mansion while Jonathan was gone? Energy. If you don't eat, what happens to your body? Well, it literally starts to fall apart, right? Because what's taken over? Entropy, chaos. Without a constant supply of energy, things fall apart. That's another way of looking at the second law of thermodynamics. To keep order, to keep things together, you have to constantly add energy. All three of those ways we talked about it mean the same thing. It's just three different ways of talking about the second law of thermodynamics. Questions? Yeah.
The sun is always giving us energy. How are we right now?
Well, you're saying as a universe, how's the energy universe running out?
Well, the sun gives the earth this energy, and the sun is going to be here for quite a while.
Yeah, but what's happening to the hydrogen on the sun? Yeah, and it's going to run out eventually, right? The amount of useful energy in the sun is finite. The sun will go out eventually. It won't be there forever. None of us need to worry about that because it's huge. But eventually, it's not going to be there. Okay? The hydrogen on Earth is slowly becoming what? What's the hydrogen on Earth getting turned into as it fuses and gives off light and heat? What's the hydrogen becoming? What element? What's 1 plus 1, guys? 2. Okay, and what's element 2? How about helium? Okay? Eventually there won't be any hydrogen left. It'll be helium. And the helium's not very good at giving us energy. It's gone by its own thing. And we're not talking in our lifetimes. We're not talking about in your kids' lifetimes. But we're talking way on down the road. Millions of years, probably. I've seen several different numbers, but nothing you need to worry about. We're not, well, we're all dying, but not because the sun's going to go out on us. All right, another quick 2 terms here. You don't want to write this down. Just here, there's 2 things you need to know here, 2 big ideas. Everything we do in nature, in living things, is chemistry, right? We've talked about this before. Everything you do. If you look back there at Brian and you say, I just really don't like Brian very much. Yeah, sure. How many of you do that? Let's take a poll.
Brian?
Yeah, you just look at Brian and you just don't like
All day, every day.
Okay. That's a chemical reaction. There's something that just makes us not like Brian. Could be his teacher. I don't know. But there's something going on with Brian that's causing that to happen. That's metabolism. Okay? It could be that he's giving off some really weird pheromones, right? That could be part of it. Okay? It could be that. Okay? Could be his effect on women, right? This could be a pheromone. You know, I don't know. Okay? But regardless, he put his, I'm just getting back to what he did in my yard. Don't believe you. Don't believe you. Anyway, back to what I'm saying. Everything we do is chemistry, and all those chemical reactions make up our what? Our metabolism. That's nothing new. We've talked about that before. But we're going to break our metabolic processes down into two kinds of metabolism, catabolic and anabolic. Again, those shouldn't be new words for you. Catabolic means to what? To break down. We've called catabolic reactions, what other kinds of reactions? We call them hydrolysis reactions. Reactions that break things down. Typically, when you break things down, what happens in terms of energy? It's usually given off. There's some exceptions. Typically, it's given off. And what's our word for reactions that give off energy? It's the word we're going to use in biology for. Yeah, exergonic is the word we're going to use in here. Exergonic. Reactions that give off energy, we're going to say exergonic. So when you hear catabolic, I want you to think exergonic. They release energy. Because where is the energy stored in those chemicals? The bonds. And if you're doing catabolic reactions, you're doing what the bonds? You're breaking them, thereby releasing energy. On the other hand, anabolic means just the opposite. Anabolic is a synthesis, putting pieces together, making new what? Making new bonds, polymers. What are some other words we use for synthesis? Condensation. What's another one that you saw in your test several times the other day? Dehydration. Putting things together. Typically, in terms of energy, what do you got to do to put things together? Use it. Add it. So we're going to say that these reactions tend to be endergonic. Anabolic reactions tend to require energy to make them happen. What's the word for the energy needed to start up a reaction? Activation energy. That's the term you saw in the middle of the song. Activation energy. So these require activation energy. Energy to make them happen. And then one other point on this slide that you need to make sure you know is that very bottom idea called coupling. Energy coupling. If we use the word couple like a verb, what does it mean? To put together. If we're talking about energy coupling, we're talking about coupling what two kinds of reactions? An exergonic with an endergonic. What does the exergonic do for the endergonic? It provides the energy, the activation energy to make it happen. What exergonic reaction in your body provides the energy to make almost all the body's endergonic reactions happen? Okay, I heard two things, both of which are correct. ATP what? ATP hydrolysis, which means taking ATP and breaking it apart and thereby giving off energy. That energy is then used by what? The energy released by ATP hydrolysis is used to make the endergonic reaction go, right? Now, Hayden said something about phosphorylation. That's another word from the Moodle assignment. What does that mean? Adding a phosphate to something. A phosphate that typically comes from where? From ATP. And what does it take with it to that thing that's getting added to? Energy. So it's a way to transfer the energy. Phosphate groups tend to transfer energy. But regardless, this idea of coupling. First you get an exergonic reaction. Usually it's ATP hydrolysis. That provides what? The activation energy needed to make what happen? Endergonic reaction. That's what coupling means. To make an endergonic reaction happen, first what's got to happen? Exergonic reaction. Does that make sense? Let's talk a little bit about ATP. This should be reviewed for the most part. You know what it stands for, adenosine triphosphate. It's what kind of chemical? What are those 4 macromolecule types? It's a nucleic acid. What are the building blocks of nucleic acids? Nucleotides. And remember, nucleotides are built from 3 pieces. What are those 3 pieces that build nucleotides? Yep, I heard all of it. Sugar, that's always in the middle. What's the sugar involved with ATP? Ribose. The same one found where? RNA. Same sugar we find in RNA, ribose. What's the nitrogenous base in ATP? Adenine. And then there's how many phosphates? 3. So it's a sugar. Let's just look at a picture. Here's ATP. What part am I circling right now? That's the sugar. That's the ribose. Always in the center. That would have to be, therefore, what? That's the nitrogenous base. That's the adenine. And then here are the 3 phosphates. Now, remember that ATP gives off its energy when it's what? Yep. And the word for that is hydrolyzed. When it's hydrolyzed. When we hydrolyze ATP, what's the only bind that's usually broken? That one right there. When that bind is broken, that energy is given off. Usually the phosphate is transferred to something else. Maybe to an enzyme, maybe some kind of protein. And when it's transferred, when it phosphorylates something, it provides it with what kind of energy? Activation. The energy to make something happen. Notice, this is trying to show you that ATP gets broken down into ADP and P. And that when that happens, when it's hydrolyzed, that provides the energy for all your body's endergonic reactions. Things like protein synthesis, nerve conduction, muscle contraction. The hydrolysis of ATP, the breakdown of ATP, provides the energy for those things to happen. Talked about this analogy before. I want you to think of ATP like a charged up battery. The battery that runs your body. If ATP is a charged battery, ADP and P would be what? A dead battery. But a dead battery capable of what? Being recharged. What process recharges your batteries? Cellular respiration. And the energy to recharge those batteries comes from where? Food energy. So what we're seeing over here on the other side is this is cell respiration over here. Cell respiration recharges your ATP, it rephosphorylates the ATP, it puts these 2 things together, ADP and P, we're back to ATP. It's a cycle of hydrolysis followed by condensation or synthesis. That's the ATP cycle. Does that make sense? All right, let me back up a slide. A scary thing about ATP is that you only store enough of it in your body for about 20 seconds. So if you stop doing cell respiration, you've got about 20 seconds. If you run out of ATP, what happens? You die, and you're not coming back once you run out of ATP. Why? That doesn't seem like that makes sense. Because we said before, our bodies are pretty conservative. Typically, we plan ahead, right? Why don't we plan ahead here? What's going on with ATP that makes it not very storable? There's several ways we could say it. It's really reactive. And the hydrolysis of ATP is what kind of reaction? Spontaneous. It's one of those things from the Moodle song, right? Spontaneous means what? Yeah, and it happens how? On its own. Okay. Now, spontaneous doesn't necessarily mean it happens on its own really fast. It could mean it happens slow, like a car rescue. That's spontaneous, right? That happens over a period of months or years. But ATP hydrolysis is spontaneous and what? Spontaneous and fast. You can't store it for very long. How do we store energy we want to keep for later? Fats, or maybe glycogen, right? Not ATP. It's not storable. So again, ATP hydrolysis is a spontaneous reaction. It happens on its own. It doesn't need what? It doesn't need activation energy. It happens on its own. Is it exergonic or endergonic? ATP hydrolysis. It's exergonic. It does what with energy? Releases it. Gives it off. Well, yeah, but it's surrounded by water, right? So it's not like it's, I mean, it's in a living thing. So water's always there. The key thing is energy doesn't have to be added. Let's come back to that slide later. Now let's talk about this equation stuff. You should have one of these little handouts that I gave out on Friday. A little problem on it. If you don't, hold up your hand and I'll give you another one. Now I'm hoping that you caught a pattern from the last test. Things that are on these little handouts, where did they show up?
Everywhere.
They showed up on every test and quiz. So you might want to know how to do this, because it's going to show up. It's easy. It looks kind of intimidating. It's really not that bad. We'll put the equation up here on the board. Equation for what's called Gibbs free energy. First of all, you got to know what free energy is. It's the energy that's available to us to do what? To do work. Or we might think of it this way. The energy available to make what happen in our bodies. What kind of reactions? No. It's the energy available to make our endergonic reactions happen. We might think of it as another word for what kind of energy. I think that's there for you. Activation. We're going to use those two words to mean similar things. Activation energy and free energy. Energy available to allow our bodies to do work or to make endergonic reactions happen. Now the equation looks a little bit intimidating, but the math is pretty easy. Instead of writing out the word delta, what symbol means delta? A triangle. We actually use it in physics and chemistry to mean what? Change in. So this equation is a change in free energy. G's our symbol for free energy. And that's equal to a change in enthalpy. Now it's very easy to confuse enthalpy and entropy. Don't confuse those two things. Enthalpy is the total amount of what? Not so much heat. Total amount of energy available in the body. Total energy. Enthalpy. Depending on what you're talking about, it can be heat. But in this case, we're not thinking of it as heat. We're thinking of it as chemical energy mostly. All right, and then the next part of the equation, minus T. And that's the temperature. The temperature has to be in what for this to work? It's the Kelvin temperature. And then the delta S part is the change in what? Entropy. Remember, entropy is disorder. Now there's several things to know about this equation. I think we'll work the problem first, and then we'll talk about some issues and some things you need to know about it. Yeah?
Are we going to use like different equations to solve what this is?
This is probably the only one you're going to need to know for this class. It's going to be much more simple than what you did in chemistry. Yeah, if you take chemistry, I'm sure you got pretty deep with this. We're going to keep it simple in terms of free energy. All right, so here's our equation we're trying to solve for delta G. If you read through the problem there, it says the enthalpy is 56,000 joules per mole. So we're just going to plug that in for delta H. 56,000 joules per mole minus the temperature. Now, in this problem, they give us temperature at 20 degrees C. In Kelvin, that would be 293. Add 273.
It would have to be in Kelvin.
Has to be in Kelvin. It's the absolute temperature. Now, there's one thing that they should have given you in this problem that they didn't. It says that up there that delta S is what? 178 joules per mole. Let's plug that in for delta S. But what's missing? What's going to be weird about this because of the units? The kelvins aren't going to cancel out anywhere. Really, this ought to be joules per mole times Kelvin. So whoever wrote this question, he should have put in times Kelvin up there. The kelvins are going to cancel out. So we're going to be left with joules per mole. Now we need to go through and do the algebra. So 293 times 178. $52,154, right? All right, and then we'll fill back in the front. So it's 56,000 minus 52,000. So when we do the math, we end up with delta G equal to 3,846 joules per mole.
And that guy's video is units.
So again,
That guy's video is units of kilocalories.
kilocalories is just another unit for what? Joules and kilocalories both measure what? They're energy units. So you can do it either way. They're both energy units. We're going to leave it right there. We're going to leave it right there. As far as we're going to go. Now, the numerical value, you need to be able to calculate that. That's easy. But more important for us is what about that number? Is it positive or negative? This one's positive. If you get delta G to be a positive number, that means that to make whatever reaction we're talking about here happen, what has to happen? You have to add that much energy to make it happen. Which means this is what kind of reaction. We have to add energy to make it happen. It is endergonic. And another term that we're going to use is what? Not spontaneous. Non-spontaneous. So if you don't understand that, you need to write this down. If delta G is a positive number, that means the reaction that you calculated delta G for is endergonic and non-spontaneous. Positive delta G. Endergonic, not spontaneous. That 3846 would be what kind of energy? The activation energy. It's the energy required to make this protein unfold the way it's unfolded in this particular problem. Does that make sense? On the other hand, I think the problem on the Moodle assignment, you came up with a negative delta G, right? Did the same thing. I think the problem in the Moodle assignment, you should have come up with a negative number. If you get a negative delta G, that means what?
Spontaneous and it's exergonic.
Right. It's exergonic because the negative is telling you what about the energy? What's the negative in front of the energy number mean? It's being released. It's being given off. So energy is being released, so therefore it's an exergonic reaction, and it's also what? Spontaneous. So again, if you get delta G to be a negative number, that reaction is exergonic and it's spontaneous. It happens on its own. That's as deep as we're getting with Gibbs free energy. Does that make sense? We could go way, way deeper, and you guys that have been in basic chemistry know that. That's as deep as we're going. That should not be hard math, correct? Nothing difficult there. Everybody in here can do it. It doesn't take Einstein, all right? All right, going forward. This little diagram that's about to pop up on the screen, hopefully, is just to remind you about coupling. Let's get it up there first, and then we'll talk about it. This is trying to show you that the reaction down here on the bottom is what kind of reaction? What kind of reaction must that be? Endergon. It needs energy. And where's the energy coming from to make it happen? ATP hydrolysis, right? These are coupled together. This one will not happen without energy from that one. That's what coupling means. Does that make sense? So almost all of your body's endergonic reactions are coupled with what? ATP hydrolysis. One thing I'll just mention, because it shows up occasionally on AP exams, ATP's chemical cousin, GTP. It's essentially the same molecule with what instead of what? Guanine instead of adenine, but still it's really good at what? Transferring energy, right? So if you might talk about GTP hydrolysis. Same, just think of it as exactly the same as ATP hydrolysis. Provides energy.
But that made them build up breaking off though or not?
It's specific parts of your body. It's not nearly as common as ATP. It's only in certain parts. Yeah, third cousin by marriage or something like that. Yeah, I'm not sure. Maybe some inbreeding going on. Here's another slide just to remind you about coupling. This is showing you that muscle contraction is endergonic. It takes energy to do that. Anyway, to make your muscles contract, what has to happen first? ATP has to be hydrolyzed to provide energy to make it happen. Those two processes are coupled. Muscle contraction will not happen without ATP hydrolysis. Captain, you want to get up in front of the room and do that? Come on up and demonstrate for us. All right, now before we go further, this week's going to be weird because of Wednesday and all that PS or plan and ASVAB and all that other stuff. That's up to you. I'm not going to tell you when I'm being recorded not to come take the ASVAB. You should come take the ASVAB. It is very important. That's on audio now. But regardless, the next big topic is about enzymes. And we're going to get to another lab. Next week we'll be in the lab most of the time.
Oh, yay!
You need your lab book because everything we do in the lab will go from here on out in that lab book. And we'll talk about the format of that later in the week. You're going to have to make a poster for this lab, like we did in the first one. There's two parts this lab will do. The first part, I'll give you a set of directions to say do A, B, C, D, E, F, G, see what happens. The second part of the lab is you'll have to decide on an independent variable, and you will have to design and then do the experiment. And then write that up. That's where we're going. Try to do most of that next week. What we want to try to get through this week is some basic stuff about enzymes, because the whole lab setup is about enzymes next week. When you hear the word enzyme, the very first thing I want you to think about is what they're made out of, which is what? Proteins. And then I want you to think about what causes the proteins to be made the way they're made, and that would be DNA. So DNA to protein to enzyme. Think that way. A lot of people have missing or non-functional versions of some enzymes because they have what? Mutations. And if you're missing certain enzymes, that means you're probably not able to do what? Certain kinds of chemical reactions, right? They're probably not working in you the right way. Like lactose intolerance, for example. That one's a kind of a benign one, right? I mean, that doesn't really hurt you much. But there are some that can be very serious, like Tay-Sachs disease, like sickle cell anemia, the protein deficiency. We'll get deeper into that when we get into genetics. But for right now, also think when you hear enzymes about enzymes being catalysts. If I said that Hayden is a catalyst for evil, what does that mean? He causes evil to happen, right? So make it happen. We also can think of it as not only make it happen, but do what with it? Speed it up as it's happening. So cause to happen quickly. Catalyst. That's what enzymes do. They catalyze things. They do that in a number of ways. And we'll get to the different ways they do it next time. But one thing I want you to definitely think about when you think about enzymes is they catalyze reactions by decreasing the amount of energy that you need to start a reaction. They decrease activation energy. They help reactions happen in your body with less free energy. They help certain reactions in your body happen with less free energy. And again, we'll talk about how they do that later. Now, we've talked over and over again about enzymes being proteins. And we've talked about how the shape of a protein is hugely important because structure determines function. And we talked about the different levels of protein structure. Just as a quick review of that. The most basic level is primary structure. And that's basically what? Which amino acids and what order are they in? That's completely determined by DNA. And what holds this amino acid to this amino acid? Peptide bond, which is what kind of bond? Covalent, and it's a bond between what two functional groups? Amino on one amino acid to the carboxyl of another. Very nice. What comes next? Secondary structure. And that's how our certain sections of a polypeptide shape held together mostly by hydrogen bonds between polar amino acids, polar R groups. Next is how is that in one entire polypeptide shape. The overall shape of a whole polypeptide, and that is called tertiary. Why does it bend the way that it bends? Let him answer the question on that. It bends the way it bends largely because of hydrophobic amino acids wanting to be where? Inside, away from water, and hydrophilic ones needing to be outside, near the water. But once it gets all bent and twisted, what holds it this way? Disulfide bonds and hydrogen bonds. And what's the amino acid you need to know the name of that has sulfur in it? Well, that's the group. What's the name of the amino acid? Cysteine. There's some others. Cysteine's the one that comes up a lot. And then finally, the overall shape of your protein, quaternary, is how these different polypeptides all wrap together. And that's held in place by all kinds of forces. Hydrogen bonds, van der Waals forces we talked a little bit about last time, and all kinds of stuff. When we get in there, though, and start talking about the nitty-gritty of enzymes, that's an important word to know, substrate. The substrate is the chemical that an enzyme acts upon, the substance that an enzyme acts upon. For example, we've talked several times in here about amylase. Where would you find amylase? It's also in your intestines. But what does amylase act on? Starch. Starch is the substrate for amylase. Amylase will take starch and break it into simple sugars. So the substrate for amylase, starch. Another enzyme we're going to use in the first part of the lab we're doing is called catalase. We mentioned catalase in here a couple of times for different reasons. What's the substrate for catalase? We talked about this back when we talked about organelles. There's an organelle where you would find a lot of this at. The organelle is called the peroxisome. And this enzyme helps to break down hydrogen peroxide. and it'll help to catalyze this reaction. Hydrogen peroxide breaking down into what two things?
Water and
What are the bubbles you see when you see peroxide being broken down? Oxygen gas. Now notice that doesn't balance. So we would need to go back and balance it out. So
Peroxidone is the substrate for catalyst.
hydrogen peroxide is the substrate for catalyst. Hydrogen peroxide. This is hydrogen peroxide. It's the substrate for the enzyme catalyst.
And the substrate, like,
It's what it works on. It's either what it breaks down or what it puts together. Could be either way. Another thing I'll go ahead and mention here. A lot of people, when they hear the word enzymes, what's the one kind of enzyme that comes to their mind? If Emma went home and asked her dad about enzymes, to name an enzyme, what do you think he would say? It's probably going to talk about something to do with digestion, right? That's what most people think, right? Digestion. Breakdown. But remember, there are just as many, well, maybe not just as many, but probably just as many enzymes in your body that do anabolic things as do what? Catabolic things. A lot of enzymes cause synthesis, condensation reactions. Other enzymes help to catalyze hydrolysis kinds of reactions. But remember, it's not one or the other. Some do one, some do the other. They're not all digestive enzymes. There are all kinds of enzymes in your body. Another important term to know when we're talking about enzymes is what's called the active site. That's a groove on the enzyme with a very specific way. The groove on an enzyme with a very specific shape. And also a very specific, well, yeah, that's what I'm going to keep reading on the slide up there. A very specific shape and a very specific charge, an electrical charge, positive, negative kind of charge. The active site is where what two things get together. It's where the substrate binds to the enzyme. Substrate and active site bind together at this point called the active site.
the substrate.
And the enzyme bind together at this place called the active site. Now the terminology is sort of changing in terms of the way they describe this, but for many years they said the fit between the substrate and the active site was like a lock and key. And that's still a good analogy. With what being the lock? The active site would be like a lock, and what would be key? The substrate. Now, here's the deal. If that's why the active site has to have this very specific shape, because if the substrate won't fit, what can't happen? The reaction can't happen. It's very, very specific. How many of you have ever been to Walmart and got a key made, and you got back and it stuck it in the lock and it didn't work? I've been that a next time. You went to get like a house key made, and you get home and you stick it in there, and it sort of fits, but it won't turn. If you're too lazy to go back to Walmart and get them to remake one, what do? You may hold it up to the original key, look at the little grooves on it, and do what? Take like a file and file it off so that it's exactly the same shape. It turns out that sometimes your enzymes can do that, because once the substrate fits in there, the enzyme will slightly change shape. It may do this number and squeeze in on that substrate, or it may kind of do this number and pull out on it. If it's squeezing in on the substrate like this, what do you think it's probably trying to make happen if it's pushing in on the substrate? This is the active site. And these two pieces go in there. They fit in. And then my active site does that. What do you think it's trying to make happen when it does that? It's probably trying to make those two things go together, right? It's probably a synthesis kind of reaction. If on the other hand, these two pieces go in, and my enzyme sort of does that, it's making hydrolysis happen, right? Sometimes that's called an induced fit. that the enzyme, the active site, actually can slightly change shape to make the reaction happen. That's one of the ways enzymes work. Is that active site can have slight changes in shape to either push substrates together or possibly pull them apart. Again, it's called an induced fit. We'll talk more about that next. Key thing to know right now: substrate is the substance acted on by an enzyme. For it to work, it first has to bind to the active site. Their shapes have to be very similar. They fit together like a lock and a key. Not just their shape, but also their charges. They have to be complementary. Once they get together, the substrate and the active site, what's supposed to happen? Some kind of reaction. It's supposed to catalyze a particular reaction. Probably the last slide we will look at today will be this one. This sort of summarizes what's going on. Now, notice you got two different things going on here. Over here it says degradation. I don't know that we've used that word. What word have we used instead of degradation? Hydrolysis, or in terms of metabolism, we use the word catabolic. So that's hydrolysis or catabolic over there on the left, and over here on the right, it's synthesis or condensation or dehydration or anabolic. You see that enzymes are involved in both. Oftentimes we'll write this out in words, that you start with an enzyme plus a substrate. You can see that going on here, enzyme, substrate. Notice how the shape of this is complementary to the shape of that active site. They have to fit, that whole lock and key thing. Once they fit together, this is where the magic happens, right? You have Barry White playing in the background or something, right? We call that the enzyme substrate complex. So that's where the chemical reaction is catalyzed, when they're together. But notice, after it's catalyzed, they come apart. And we end up with an enzyme plus some products. What do you notice about enzyme, enzyme, enzyme? It's not changed. Which means what about your body's enzymes? What? Yeah. And perceptive. If they're not changed, what does that mean about them? They can be used over and over and over and over. They're recycled. That's a key thing to know about catalysts. Catalysts help to start a reaction, but they don't actually what? Like chemistry people. Catalysts take part in catalysts help to start it, but they're not actually involved in the actual reaction. They're not changed by it. There's no chemical changes happening to the enzyme. It's more of a physical kind of thing. It precipitates chemical things to happen to the substrate, but it itself, the enzyme itself, is not chemically changed. So it's used over and over and over again. The example we just looked at was a hydrolysis kind of thing and a catabolic kind of thing. But here's the same thing in terms of anabolic stuff. Here we've got an enzyme, two substrates in this case. Enzyme grabs onto those two substrates. Here's our enzyme substrate complex. That's where the magic is happening. And eventually, they come loose. The enzyme is unchanged. And we've got a product. A product that is different than what we started with. Make sense? Like it. All right, I guess we'll go ahead and look at this one. A little bit ahead of where we were last. What? We said enzymes lower activation energy. Here's 3 different ways they can do that. Before you start to try to write too fast, let's think for a second. Let's say that these two things right here are substrates, and they're floating around in a huge container, maybe in a swimming pool. They're floating around in a swimming pool. They're actually really, really tiny atoms floating around in a swimming pool. But if they get close to each other, they'll react. Right now, they're just floating around. What's going to determine whether or not they react? What's got to happen before a reaction takes place? They have to collide. Reactions are about collisions. What parts are the outside parts of these atoms? The valence electrons. That's why valence electrons determine what? Yeah, what will react with what and how it will react. It's all about, because they're the outside parts. If we had these things swimming around in a big pool of water, what can we do to make them react faster? To the water. What can we do to the water to make them react faster? Heat it up. What would heating up do to make these things react faster? Well, they're moving fast, which means they're more likely to what? Collide. But they not only have to collide, they have to collide how? The right orientation. But maybe they'll, let's rearrange this a little bit. It's the most useful thing I ever got at Cracker Barrel.
Did you like buy them and it's like, hey, I can make a lot.
Yeah, I just thought, hey, I can use that for a lot of stuff. So yeah. So these things are floating around. If they collide like this, something might happen, right? But if they collide like this, is anything probably going to happen? No. So they have to collide with the right orientation. How's that determined just in normal nature with no enzymes involved? They just float around in a pool. What determines if they collide that way or not? Luck. Okay. Now, if you increase the temperature, you increase the chances that what? They will collide this way. But still, if there's only a few of these and a few of these in a pool of water, what are the odds that they're going to not only collide, but collide the right way? Slim. So how can we up our chances without involving enzymes at first? We can heat the water up. What else could we do to up our chances that they'll collide like this? Add more. Increase what? The concentrations of the substrates. More substrate concentration should mean more likely that what will happen? They will collide. So those are important ideas to think of at first. Faster, hotter temperature means faster motions, more collisions. And more concentration, I mean, think of it like on a road. You're more likely to have a car accident on an abandoned country road or on an interstate. Crowded interstate in Atlanta at rush hour. Probably in Atlanta at rush hour because the concentration of cars is more likely, is higher, and therefore you're more likely to collide with something, correct? Enzymes. Hello? Come on in.
Thanks, abruptly, right?
That's okay. What you got?
I've got invitations for the check ceremony.
Ah, I can do that.
Thank you.
Catherine. Jackie. Hayden. Amber. And Savannah. They get some invitations when you can bring them. I think it's your AP thing from last year. At least what that's for. Anyway, let's wind up. Actually, we're probably not going to even have time to get into this today. Reminders, real quick. This afternoon, study session. Tomorrow morning, study session. Don't forget about those. I need to get Moodle number 7 over here on the desk. Don't forget about Moodle number 8 this Friday. It's about the same. It's about the same. One thing about Moodle 8. One thing about Moodle 8. Moodle 8 includes a free response question. 60% of your grade for Moodle 8 will be based on that free response question. Do not leave it late. 60%. Friday. Friday.
Yeah.
Well, yeah. Maybe it will be Tuesday.